Energy in Reactions, Part A of our Unit 7 notes. We're starting by investigating how can we speed up a chemical reaction. That's what Part A is all about. And the first part of understanding that is understanding that energy in chemicals is stored within chemical bonds. So in order to modify energy, we're going to need to break and reform those chemical bonds. The law of conservation of energy sounds a lot like the other two laws of conservation we've learned about already. It states that energy can be converted from one form or the other, but it cannot be created or destroyed. Can't create or destroy it. We can only change what it looks like. In chemistry, so kind of connecting your physics knowledge to chemistry, potential energy is stored. That's what's found in chemical bonds. All potential energy is stored energy. And then kinetic energy, which is the energy of movement, is in the form of heat or temperature, which you've already seen in our gas tube. We know that by changing temperature, we can cause certain things to occur. And then you can see the image on the right is just an example of the actual how much energy is stored within chemical bonds. So you can see that in single bonds, there's a certain amount. We can actually measure per mole how much energy is stored in calories. And in double bonds, we have even more energy stored. So a double or triple bond stores more energy, more potential energy than does a single bond, which means it's going to be harder to break. It's going to require more energy in order to break that bond. Energy can be written as a term in a chemical reaction equation. This is going to end up being really important. We've seen chemical reactions a lot so far. What we want to start doing is adding our energy, adding the E in the equation. It really makes a big difference whether our energy is a reactant or our energy is a product. Let's investigate. We call a reaction with energy that is a product exothermic, an exothermic reaction. That means energy is exiting our system. It is leaving. It's a product. In a reaction where our energy is a reactant, we call it an endothermic reaction. Energy enters. So let's keep using these terms endo and exothermic to kind of investigate what's going on. So in exothermic reactions, excess energy from breaking chemical bonds exits as a product. These reactions release energy as heat, light, sound. Good examples are things like fireworks exploding, fusion happening in the sun, any combustion reaction that heat is produced. So your car engine being turned on, lighting the stove, lighting a Bunsen burner. We know that something like a firework, we can see and hear the energy being released. We hear the bang, we see light, and there's heat as well. Those are exothermic reactions. We can see or feel or measure the energy exiting that particular chemical reaction. An endothermic reaction is the opposite. So these reactions absorb energy, becoming colder. And that happens because energy is needed to enter with the reactants in order to form higher bond energy products. So my products have more energy stored in their bonds than my reactants. So examples are if you mix Country Time lemonade powder into water, it becomes cold. If you mix baking soda and vinegar, it gets cold. You could even do that at home if you wanted. And photosynthesis. Photosynthesis is a reaction where plants take carbon dioxide and water in, and they form sugar and oxygen. And that's an endothermic reaction. It's actually forming that sugar that it's forming has more energy stored in its bonds than either of the two reactants. So that's my endothermic reaction. So this is just a really good picture, and this is in your notes. I really appreciate kind of the visual here. When we're actually doing this in the lab or when you're testing it out, we know if something is endo or exothermic because it either gets warm or it cools down. So it's easy to tell when we can actually mix the chemicals. It's a little more complicated when we don't have the chemicals to actually mix and measure. Or if the change is so small, it's hard to measure with a thermometer. So go ahead and pause here and try out questions A and B. When the baking soda and vinegar are mixed, the beaker reacts to feel cold, which means it's endothermic. Energy is entering, it feels cold. And question B, we have sulfuric acid and magnesium, but that doesn't matter. We see energy as a product. Energy as a product means something is exothermic, exiting energy. Part 2, collisions cause reactions. This is a very logical something, so hopefully this sounds kind of familiar to you. This is called collision theory. Basically, in order to react, they need to actually collide, right? The reactant molecules need to interact with each other in order to form products in the first place. If you never mix the baking soda and the vinegar, they're never going to react, right? So because we can't create or destroy energy, according to the law of conservation, If potential energy is released, it becomes kinetic energy. So that means if we break chemical bonds, it's going to be released as heat or motion or sound or light. If kinetic energy does work, it can become potential energy. So that would be where we would form stronger or higher energy chemical bonds as potential energy. But the gist of this is, in order for our reactions to occur, the reactant particles need to collide, right? They need to mix together in order to be able to form any products. Makes a lot of sense. Particles colliding, so that's kinetic movement energy, can result in either or both new chemical bonds or a release of energy from breaking chemical bonds. If the reaction releases extra kinetic energy as heat, light, sound, it's exothermic, right? We can see the energy exiting as a product. If the reaction absorbs extra kinetic energy, it's endothermic. So it's absorbing that extra motion to store in new chemical bonds. So more collisions mean more opportunity for successful collisions. So if we want to increase the rate of a reaction, if we want a reaction to go faster or to go at all, we want to do things that are going to increase the amount of successful collisions that are going to form a product. So the molecules need to hit each other in the right way, and they need to hit each other with enough energy to actually cause products to form. That's the goal. So we reach that goal by 3 different mechanisms. If we want a faster reaction, or if we need the reaction to go at all, we need to increase particle collisions. So reaction rate is a term. It is how fast a chemical reaction goes. These 3 things affect reaction rate by speeding it up, by causing more particle collisions. The first is the concentration of the reactants. The more molecules, the faster they're going to react with one another. That makes sense. If you have a bowl full of nuts and bolts and you need to combine them, the more nuts and bolts you have, the easier that process is going to be. Temperature. How warm it is. You guys told me this in the gas tube demonstration, that as we heat something up, the particles move faster. So if the particles are moving faster, they're going to collide more and they're going to collide with higher energy. Both of those are good for increasing reaction rate. And the third one is a special chemistry one. That's a catalyst. A catalyst is a special chemical that increases the rate of a reaction by lowering what's called activation energy. The catalyst it's a chemical bystander. It doesn't do anything, but what happens is it provides the reactants with kind of a different alternative to form products. And we'll see examples of these in class later on for what each of these 3 things does to increase reaction rate. So pause here, try out C, D, and E. C, adding a catalyst to the decomposition of hydrogen peroxide would speed up the reaction. We add a catalyst. Note, this is an exothermic reaction. The E is a product. D, using ice instead of liquid water for the single replacement reaction between sodium, metal, and water. If we use ice that's colder instead of liquid water, it's going to slow it down because what we've done is we've decreased the temperature. If we've lowered the temperature, we're going to slow it down. And finally, using less diluted aqueous solutions in a double replacement reaction to form something new. If we use something that is less diluted, what that means is that there is a higher concentration. So let me write that down. That's higher or increased concentration. And we know that if we increase the concentration, there's more molecules. It's going to speed up our reaction. Alrighty, it's time for part B, chemical equilibrium. You guys have some experience with this already from the gizmo, so let's dive right in. We are answering, how can we make more products when our chemical reaction can go backwards, right? We have these reversible reactions, so how do we get the most products if the reaction can go in both directions? So let's start by reviewing our reversible reactions. Can chemical reactions go backwards? Yes, we learned that, but only some can go backwards. These special chemical reactions are reversible. We use a special reaction arrow to indicate this. So you can see we've got our reversible arrow here. Instead of our typical chemical reaction arrow that looks like that, we've got our 2-way arrow to indicate it's not a normal chemical reaction. It's a reversible reaction. In a standard chemical reaction, so non-reversible, where we have our single arrow, we begin with all reactants and no products. The reactants then collide with each other and transform into the products. When one reactant is used up, the reaction stops because it can't make any more product. We end up with nearly all products, maybe some leftover reactant if we had extra of one of them. That's in a standard chemical reaction. So how is that different from a reversible reaction. In a reversible chemical reaction, we begin with all reactants and no products still. The reactants then collide to transform into products, but here's the difference. The rate at which the reactants transform into products will begin to decrease over time as the concentration of the reactant decreases. So as we use up more of the reactant, it slows down how fast it's making product. At this point, some of the products will then begin to revert back into reactants. That's something that would never happen in a standard chemical reaction. It's got to be only in a reversible chemical reaction. What we end with is not all products. We end with some reactants and some products that are, and this is important, constantly being made. Constantly being made. Let's investigate that constantly being made. That process is called dynamic. Chemical equilibrium is dynamic. That means constantly changing. But to us, what we see is we don't see anything happening. It looks the same to us, but we can't see molecules. Our eyes aren't that good. What happens is the molecules are still rearranging. We're still forming products, we're still forming reactants, but we're forming them at the same rate. Let me show you this little GIF that says a good job of kind of showing it here. We're constantly reforming, but because the amounts are the same, we see it as looking the same. Chemical equilibrium is the point where products and reactants are being made at the same rate. That's a definition for you. Being made at the same rate. Once a reaction reaches this equilibrium, the overall concentration of reactants and products does not change. These concentrations are not likely to be 50% reactants and 50% products. It's a common misconception, but that's very, very unusual. We don't usually see 50-50. We see whatever is appropriate for the reaction. Chemical equilibrium is dynamic because the products and reactants are still being made, but they're just being made at the same rate, so the overall concentration doesn't change, so we can't see anything occurring. The equilibrium balance point is known as K. K is the equilibrium constant. You learned about this in the gizmo. When K is greater than 1, it means the natural equilibrium position has a higher concentration of products over reactants. So maybe at equilibrium, we've got 70% products, 30% reactants. Maybe we have 51% products and 49% reactants. Maybe we have 99% products and 1% reactants. That would mean K is greater than 1. When K is less than 1, my natural equilibrium has a higher concentration of reactants. So maybe we only have 10% products, but 90% reactants. And we can calculate K by dividing the concentrations of products over the concentration of reactants at equilibrium. So we can calculate K, and we can also look up K for most common reactions because people have already done that work for us. So here are some good visuals. Let's look at our first one. In both cases, we're starting with reactants. So we can see my reactants and products. We're starting with no products, right? We're starting at 0 for products. But over time, as my reaction reaches equilibrium, it kind of levels out. So something where we have a K that's greater than 1, over time what happens is there's more products than reactants once we've reached equilibrium. Whereas if there's a small k, K is less than 1, once my reaction reaches equilibrium, we have more reactants and fewer products. When my rates flatten, it means that we've reached equilibrium because we're creating reactants and products at the same rate. Those overall amounts are no longer changing. Le Chatelier's principle. Let's talk about Le Chatelier's principle. This is probably one of the simplest, most scientific things we can learn. Le Chatelier's principle states when a system at equilibrium is stressed, the system will shift to make more reactants or products so as to undo the stress. So what does that mean? We can see here that we have a system at equilibrium, but if we increase the amount of reactants, so we stress our system, my system's going to try to make up for it by converting some of those reactants into products. That's what it's going to try to do. So let's watch. And then it's reached its same equilibrium again. Over here, if we increase the amount of products, it's going to try to undo the stress. Now there's too many products, it's messed up equilibrium, so it's going to reform some reactants instead. And here's a nice summary table for all of that. So let's just read through this real quick. So it depends on the stress. If we increase the concentration of a substance, what shift happens? Well, it's going to shift away. What does that mean? That means if I add more reactants, it's going to produce more product, which is a shift away. If I add more products, it's going to shift away to form more reactants. Let's have a little sample equation here to kind of give us an idea. So if I increase the amount of X, my system is going to make more A and B. It's going to make more products to try to undo that stress. Whereas if I add more B or A, then I have too many products. I've messed up equilibrium, so my system is going to reform some reactants to try to make up for that. So that's a shift away. That's what that first one means. The second one, what if I decrease the concentration of a substance? Well, let's say I take away some Y. Then we're going to see a shift towards the substance. So we're going to see this shift toward whatever was taken away. We're going to reform some reactants to try to make up for what happened. The same thing would happen if the opposite. If I took away some of my product, then we're going to see a shift toward my substance. We're going to reform some products to try to make up for that. That's what that towards and away means. Now the bottom is temperature. Temperature forms the exact same response. All that matters is where is the E in the reaction. So if I have a exothermic reaction, so I have my E as a product, if I increase it, we're going to see a shift away, same as we would with the concentration. If I have the opposite, where I decrease it, we're going to see a shift towards. So that's how we kind of connect our change in temperature to our shift in equilibrium. This is Le Chatelier's principle. If I mess with equilibrium by stressing the reaction, it's going to try to make up for whatever I did. So this means that how temperature changes the shift depends on where the E is, right? Kind of like what I just showed you. And this is just a summary graphic for that I have in your notes that you can kind of read through. So it's telling you based on where E is, how is it going to change what my shift is? Changing the temperature is the only thing that can change K, the equilibrium constant. Changing the concentration cannot change K. Pause here, go ahead and practice. Go ahead and pause here if you want to review these two answers, 1 and 2. Here's my big true false. Go ahead and pause here if you want to review anything. And here's my last set of answers to my bonus practice. You can pause here, and that's the end of the video. Thanks for sticking with me this whole time.